So let's continue our discussion. So अभी तक हम लोगों ने बात की the cases where we had to find the Thevenin equivalent circuit of cases where your circuit A either had independent sources or dependent sources, and we have seen that the cases where we had just independent sources in the circuit A, we could actually exploit the option that we can put all these sources equal to 0 and find out the equivalent resistance through terminal A and B. That would have given us the R Thevenin, and we also determine the open circuit voltage through terminals A and B, and we get V Thevenin in that case. And in the second case where we just have dependent sources in circuit A, we have seen that in those cases we need to actually connect a probing source, which could be either a voltage source or a current source at the terminal A and B, and then by exciting the circuit using the external probe, we can determine the R Thevenin using the probing voltage and the probing current. So in this particular topic today, we are going to talk about cases where we have both dependent and independent sources in circuit A. So let's see how we can find the Thevenin equivalent circuit in such cases. So in this case, we say that the part A or the circuit A, it contains both the dependent and independent sources. So in this case, the equivalent circuit, which is the Thevenin equivalent of circuit A, will now be replaced by this Thevenin equivalent representation, where we need to find V Thevenin and R Thevenin. So in this case, we know that V Thevenin can be determined by looking through terminal A and B and find out V open circuit. But in this case, we cannot find R Thevenin by setting all the sources equal to 0 and find out the equivalent resistance. In this case, we have to use the relationship of R Thevenin with open circuit voltage and short circuit current, which is VOC divided by I short circuit. So in this case, we need to solve the circuit twice. First to determine the open circuit voltage, and then we are going to short terminal A and B, and we are going to find the I short circuit. So now in this case, by taking the ratio of the two, we are going to find R Thevenin. So let's see the details and let's solve some problems. So in this case, the V Thevenin would be V open circuit, as we have highlighted here, and R Thevenin will be equal to the ratio of the two, which we have mentioned over here. So in this case, we will compute the open circuit voltage and short circuit current. So it means we need to solve the circuit twice. That is what is mentioned here. So now, so in this case, we can use any of the techniques that we have developed so far: KVL, KCL, series, parallel, loop analysis. All these options can give us the desired open circuit voltage and short circuit current. So this point mentioned over here, it explicitly says that the option of setting all the sources equal to 0 and find out the equivalent resistance, it is not applicable now. That is only applicable if you only have independent sources in your circuit A. So now, because we have both dependent and independent sources, we need to solve the circuit twice to find both open circuit voltage and short circuit current. So in this case, let's determine the Thevenin equivalent circuit to find out V naught. V naught is the voltage which is highlighted over here, and it is the same voltage that is across this resistor, 1 kilo ohm. So let's see how we can solve this problem. So first of all, the terminals A and B are already identified here. So in this case, this would be our circuit B, जिसको हम फिलहाल ignore कर देंगे, and we will keep the rest of the circuit, which is this one, as circuit A. And in this case, we are going to find the Thevenin equivalent circuit for this particular part, and we are going to connect the part B at the end to find out V naught. So this is the strategy that we are going to follow for our case. So in this case, let me clear this. So in this case, we can consider part A to be as simple as possible. So because we have already given what terminal A and B are, so we're going to keep these as our terminals, and then we're going to find out the equivalent circuit. So in this case, let's find out the open circuit voltage, which is represented like this. So here we are going to see through these terminals A and B, which will give me the open circuit voltage. So let's try and solve open circuit voltage, which is nothing else but the voltage across this resistor. So let's solve this problem. So if we look closely, we can see that this is a super node, because there is a voltage source connected between two non-reference nodes. So these are two non-reference nodes, and we have a voltage source in between. So we can apply the super node concept here, and we know whenever there is a super node, we can write down the constraint equation, and here we can see the constraint equation will be the voltage at this point. Let's say this is V1, and this voltage is same as V open circuit, so we can write it as V open circuit. So in this case, the constraint equation will be, let me just clear it. Constraint equation will be V1 minus V open circuit is equal to 12. So it is V1 minus V open circuit is equal to 12, and from that we can find the value of V1, which is 12 plus V open circuit. So now let's apply at this super node, let's apply KCL. So that would be sum of all the currents maybe leaving the node, sum of all the currents entering the node. It would be current entering the node is equal to current leaving the node. So let's apply KCL here. So let's say assume all the currents are leaving the node. So it's going to be, this current will be V1 minus, and because there's a negative sign here, it is minus 2kIx. So it will be V1 minus 2kIx, and we know what V1 is. V1 is 12 plus V open circuit. So this is V1 minus AIX over 1k, which is this 1k. We got it here. The current going in this direction is V1 over 2k. So this whole is V1 divided by 2k, and the current going in this direction is V open circuit divided by 2k. So this is V open circuit divided by 2k. And here we can see, because we have a dependent source, we need to write down the controlling variable in the form of node voltage. And I can see the controlling variable is this current, and we can write it as V open circuit divided by 2k. So the controlling variable is V open circuit over 2k. So you plug this value back into this equation and you solve it. This is the open circuit voltage that you will get. And we have solved this circuit once to find out the open circuit voltage. Now we are going to solve the same circuit using and then finding out the I short circuit by shorting terminal A and B and finding out the I short circuit in this case. So in this case, the whole circuit will now look something like this, and we are interested in this I short circuit, which is by connecting terminals A and B together and finding out the I short circuit in this case, and see how much current is flowing through this branch. So in this case, let's assume this terminal to be as VA, and if we look closely, we can see the voltage of this node A is also 0, because this is the reference node, and because we have shortened this path, so VA is also 0. So it means the potential across these two terminals will be 0. It means no current will be flowing in this direction. If no current is flowing in this direction, it means Ix is equal to 0. So if Ix is 0, it means this value is 0. And if this is 0, it means this source can be replaced by a short circuit. So we can write it down like this. Since VA is 0, Ix will be equal to 0. And if Ix is equal to 0, the source will be equal to 0. So in this case, this whole circuit will be reduced to this circuit. And here we need to find the I short circuit, and we can see I short circuit is nothing else but the total current that is leaving this source going into these two branches, and then it will combine in this part and it is returning to the source here. So whatever the total current is generated by this source, you just multiply it by a negative, because I short circuit is in the opposite direction. So by using Ohm's law, it is V over R, and the negative sign is because I short circuit is in the opposite direction. So I short circuit comes out to be minus 18 milliampere. So we have got V open circuit, we have got I short circuit. We take the ratio of the two to find out R Thevenin. So R Thevenin will be the ratio of these two, and it will be equal to this value. So now, so in this case, this is the actual R Thevenin value that we need to find. But if we have considered all sources to be 0 and combining all the resistances, it will give us an incorrect value, because that approach is not applicable in this case. So in this case, the solution to the problem would be, now in this case, this is the V Thevenin and this is R Thevenin, assuming that A is equal to 2K. So you put A is equal to 2K over here. So you get R Thevenin equal to 1 by 3K, and your V Thevenin is minus 6. So you either can write plus minus 6, or you could have write minus plus and then have positive sign with the voltage. So in this case, it is a problem of simple voltage division, where you can find V naught by considering this resistance in the numerator divided by sum of all the resistances into minus 6. So by solving this problem, V Thevenin, V open circuit would be 1K divided by all the resistances time V Thevenin. Okay, so let's find V naught, which is the voltage across this resistor, using Thevenin. So here we can see this should be our, at least this should be our circuit B, and we can consider this to be our circuit A. or we can consider this to be the circuit B and this to be your circuit A. It depends upon us uh, which part of the circuit we considered as circuit A and which part as circuit B. So let's assume this is our circuit A. So in this case, this resistor and this resistor is considered as part of circuit B. So these are our terminals A and B. So let me write it as A and this is at B. So in this case, let's find out the open circuit voltage through these terminals. So in this case, the whole circuit will now look like this. So this is the open circuit voltage we need to find. So this is your terminal A and this is your terminal B. So here we can see this would be your plus minus V open circuit. So here we can see we have a super node concept here because there is a voltage source connected between two non-reference nodes. So whenever there is a case like this, we need to write down the constraint equation. We can already see this terminal is V open circuit. We can name this node as V1. So we can see V1 minus V open circuit is 1000 Ix. And whenever there is a dependent variable, we can write down the constraint equation in the form of node voltage, and we can see Ix is nothing else but V1 over 2K. So let's solve this problem. So this is the Thevenin. Let me just clear it for clarity. So in this case, this is the super node. This could be V1. So we can apply super node here and apply nodal analysis. So we apply KCL at this super node. So the current going in this direction is V1 over 2K, which is this one. Current going in this direction is opposite of this. It is -1. The current going in this direction is V1, and we can see the voltage is -3. So it is V1 minus -3 over 6K, which is this one, equal to 0. And from here we can find the value of V1, which is the node voltage. So in this case, V1 comes out to be 3/4 volts. Okay, so controlling variable is V1 over 2K. We've already seen this over here as well. And now in order to find Thevenin, let me just clear it. We can apply KVL here. Maybe we can start from this point. So it would be, because the current is flowing from top to bottom, so it is plus minus. So it is minus V1, and then it is plus 1000 Ix, and then plus Thevenin equal to 0. So we have gone like this, and then from here it is back to this point. So here we can see this is the expression we have. This is the value of Ix. So we substitute Ix here. So we have V1 here, we have V1 here. We have V1 is already, we know, is 3/4. So you put those values here. From here we can find Thevenin. So Thevenin is this expression that we have seen. You can confirm this. Here V1 is positive. So you take all these values on the other side, you will get this expression. So you can verify it as well. So now in this case, Thevenin comes out to be 3/8 volts. So you have got the open circuit voltage. Now we need to find the short circuit current. So what we will do is we are going to short circuit these two terminals, and we are going to find I short circuit here now. So in this case, this is how the circuit would now look like. And now if we look closely, we can determine two things. Number one, we can see that if this is the reference node, so it means this is the reference node, this is the reference node, this is reference node, this is reference node, because all of this is one node. So in this case, we can see this node voltage V1 can be written as 1000 Ix, because this source is connected to the reference like this. So V1 can be written as 1000 Ix. If we look closely as well, the current Ix is flowing in this direction, and we can write Ix in the form of node voltage, which is V1 over 2K, which is like this. But if we look these two equations closely, we can see from here V1 is 1000 Ix, and from here V1 is equal to 2000 Ix. So how can it be possible that both V1 is 1000 Ix and V1 is 2000 Ix? This condition is only true if Ix is equal to 0. You can check it yourself. No matter what value you have over here, if Ix is 0, then both these equations are same, because here V1 will also be 0, V1 will also be 0. This condition is only true if Ix is equal to 0. So if Ix is equal to 0, V1 will also be 0, because you put Ix is equal to 0 here, V1 will be equal to 0 as well. So these are the small things that you need to remember while solving in the circuit. So for this particular case, if V1 is equal to 0, it means no current is flowing in this So this resistor is a dummy resistor, you can ignore it. And likewise Ix is also 0. If Ix is equal to 0, so it means there is no voltage source here, it can be replaced by a short circuit. So it means the overall circuit will now reduce to a simple case where you have a voltage source, resistor, and a current source, and we want to find out this current that is flowing in this direction. So you can either apply KCL or you can use superposition as well. So if you assume superposition, let's assume this current source and this voltage source is set to 0, so we can short it. So we know all the current will flow through this branch. So I short circuit will be equal to 1 milliampere. So this is the first part. In second case, we will consider it to be open circuit and only this source will be considered. So here we can see if we see how much current is flowing through it, it is V over R. So 6K divided by minus 3 volts. So I short circuit 2 will be equal to minus 3 over 6K. So the total short circuit current will be the sum of these two. So we apply KCL here, we can see it is 1 milliampere plus minus 3 by 6. So 1 milliampere plus minus 3 by 6, the answer is 0.5 milliampere. So that is the I short circuit. So now you know V Thevenin or V open circuit, and you know what I short circuit is. The R Thevenin will be the ratio of the two. The R Thevenin comes out to be 3 by 4 K. So this is not this is not where the problem is finished. We have just found out the equivalent Thevenin representation of this part of the circuit. So which is equal to this voltage source and this resistance connected in series, and then you have these two resistances connected with it. So the whole circuit will be replaced like this. So this is V Thevenin, this is R Thevenin, and 1K and 2K are these two resistances that we have considered as part B. So here we see it is just a problem of voltage division to find out V0. You plug those values here, you solve it, V0 comes out to be the solution of this equation. So again, the equivalent resistance cannot be obtained by shortening all the sources and determining the equivalent resistance, because we have both dependent source and current independent source as a part of circuit. So this is an important point to remember. So let's look at another example. Here we have a linear model of a transistor where this part of the circuit is having a voltage Vx, which is the controlling variable for the current source in this part. So this is a current source which value is GMVx, and the output terminal A and B are defined like this. So this is a case if we consider this as our circuit A, we can see there is a dependent current source and an independent voltage source. So this is the case where we have a mixed sources. So we have to find both open circuit voltage and short circuit current. So let's see. So this would be our circuit A, and this will be represented in the form of this equivalent circuit. So let's see how we're going to find out the value. So first of all, open circuit voltage will be equal to the V Thevenin, and then R Thevenin can be determined by finding out V open circuit and I short circuit. So V open circuit is voltage across these terminals, and then we will short these two terminals and we will find I short circuit as we have seen it for the previous case. So in this case, let's find out the open circuit voltage first. So let me just clear it. So in this case, we can see this V Thevenin is the same voltage that is across this resistor. And the voltage across this resistance is the current that is flowing through this resistance. So the current going in this direction would be negative of this. So this is the current, and the resistance here is R3. So R3 times GMVx with a negative sign will be the voltage across this terminal. And here we can see we can find Vx by finding out the voltage across this resistance, and it can be done by using voltage division. So you keep R2 in the numerator, divided by both resistances and into Vs. So Vx will be equal to a voltage divider, and you substitute this value here. This is the value of V Thevenin that you get. So we have determined the open circuit voltage, which is the V Thevenin that is here. It is the open circuit voltage across these two terminals. Now to find out the short circuit current, we are going to short these two terminals and we are going to find I short circuit. So in this case, this would be I short circuit, and if you look closely, let me just clear it. If we want to find out the short circuit current through this branch, the current flowing in this direction will be negative of this, and we can see since there is resistance here, none of the current will flow through this branch, all of the current will flow through this. So I short circuit will be equal to minus GM Vx. And in this case, we need to find out the value of Vx, which we have already seen in the previous case, where Vx is the voltage division across this resistor. So we substitute this Vx that we have got In this case, we plug this value here. This is the value of current that we have found. So in this case, we have open circuit voltage, we have short circuit current. We take the ratio of the two, we open circuit over I short circuit. So R3 is the Thevenin resistance that we need to find. So this is the equal to R Thevenin. So if we want to replace it with this equivalent model, so this R Thevenin is R3 and V Thevenin is this voltage that we have found out using this relationship. Okay, let's look at another example. Here we have these terminals and we need to find the Thevenin equivalent circuit of this particular case. So in this case, we need to find the open circuit voltage and then we're going to short these two terminals and we are going to find I short circuits, because in this circuit we have both independent source and dependent source available in the same circuit. So let's see how we're going to solve this problem. So in this case, we have mixed sources, and whenever we have mixed sources, we are going to compute V open circuit and I short circuit. So V Thevenin in this we can find by solving this circuit, and here we can see we have a case of supernode, and in this case we can find the constraint equation, and from constraint equation and then apply a KCL to this supernode, we can find out the all the node voltages. So first let us define a current passing through this branch, which is I1. So here we can see if we apply a KCL at this supernode, current entering the node is I1, IX and 2IX, and the current leaving in this direction will be 0 because this terminal is open. So all the currents entering the node can be written as I1 plus IX plus 2IX is equal to 0. So this is I1, IX and 2IX. This is equal to 0. And now if we look closely, we can also see that the two resistors are in parallel. So this 4K and this 4K are in parallel, and here we already know all the current that will be coming through this branch will equally divide between these two branches because both the resistances are same. So if we are given that this current is Ix, then I1 must be Ix as well, because the current must be equally divided between these two parallel resistors. So in this case, I1 must be Ix. So you can replace this I1 with Ix, and here we can see Ix will come out to be 0. You substitute I1 as Ix. So Ix plus 2Ix is 4Ix. 4Ix is 0, so it means Ix is equal to 0. So if Ix is equal to 0, let me just clear it. So here if Ix is equal to 0, it means this source is 0, because this Ix is equal to 0. It means this voltage source all this voltage source will be available at these terminals. So because here in this case, this 2Ix is 0 means this source is 0, and current source 0 means it's an open circuit. So it means you have nothing over here. So you would have open terminals here. So if you have open terminals, all this voltage will be appearing at this end. So V Thevenin will be equal to 12 volts. Or you can also consider it to be in another form where we can draw the circuit like this. It's going to be plus minus, and you have two parallel resistances like this. So this one is 4K parallel with 4K, and these are the terminal A and B. So here you can see, since these terminals are open, no current will be flowing in this direction, no current will be flowing in this direction. So whatever voltage you have over here will be available here. Whatever voltage you have here will be available here. So you have 12 volt here, 12 volt will be appearing at AB. So you can look at it from that point as well. So in this case, to find out the short circuit current, what we are going to do is we're going to short these two terminals, and we are going to find the I short circuit in this case. So in this case, this is again a supernode, and we already know that this current flowing into this is Ix, and in this case I short circuit will be equal to 4Ix. So current entering supernode is Ix, and 2Ix. Current leaving the node is I short circuit, so I short circuit is equal to 4Ix. And here we need to find the value of Ix. So here what we can do is we can apply KVL in the outer loop in this supernode case. So let's start from this point. It is 4K Ix, then it is minus 12. So 4K Ix. Ix is, this 4 will go on that side. It will be I short circuit divided by 4. So 4K Ix minus 12, and then it is I short circuit. 6K I short circuit, and then it is equal to 0. So it is this equation. So here we can see from this expression, we can find out the value of I short circuit, because there is just one unknown here, and that value of I short circuit is 12 by 7 milliampere. So we have got the I short circuit, we have got the V open circuit, By taking the ratio of the two, which is 7 kilo ohms, we can find R Thevenin. So this R Thevenin will be this, and this V Thevenin will be the V open circuit. Okay, so let's look at another example here. We have this case where the terminals A and B are these two terminals, and we need to find the Thevenin equivalent at AB. So we have to find the V open circuit across these two nodes, and we need to find the I short circuit through this branch as well. So let's solve this using the same approach that we have discussed so far. So in this case, because it's a mixed source case, so we must compute the open loop voltage and short circuit current. So open circuit voltage is across these two terminals. This is terminal A and terminal B. Let's call this node as node having voltage VB, and this node as Vx, because the voltage across this resistor is Vx. So by looking at this, the open circuit voltage will be Vx minus VB, because this is at higher potential, this is at lower potential. So V Thevenin is equal to Vx minus VB. So we need to find what Vx is, we need to find what VB is. You plug those values in, you will get V Thevenin. So if we look closely, what is Vx? Vx is just the voltage division across this resistor. So we can find Vx as this resistance in the numerator divided by sum of both resistance times 2s. You plug the values in, you get Vx. Now we need to find the VB. So if we look closely, we can find VB using KVL. So let's apply KVL. Let's start from this point. So if this is VB and current is going in this direction, so it is plus minus. So if we start from this point and have the KVL as in the clockwise direction, it would be minus VB plus this current is going through this resistance, so it is 2R times AVX, and then it is plus VS is equal to 0. And since we already know what Vx is the voltage across this, and we can find it using the voltage division as we have done like this. So in this case, VB, if we take this on the other side, it will be 2RAVX plus Vs, which is plus Vs. You plug the values in, this is the value that you will get in the form of Vs. So now we have got VB, we have got Vx. You plug both these values in this expression, you will get the value of V Thevenin like this. So this is the actual value that you will get after substitution. So in order to find the I short circuit, what we are going to do is we are going to connect these two terminals together, and we are going to find the I short circuit flowing through it. So in this case, we need to find how much current is flowing in this direction. So if we look closely, what is this? The current entering into this node is equal to this current plus this current. So if we call this terminal as Vx, because we know if the voltage across this resistance is Vx, it means this node is Vx. And since we have shortened this whole node is Vx. So we can write I short circuit is equal to, this is the current entering the node, and this is entering the node, and also the current entering the node is this one. So it is going to be plus AVX is equal to the current going in this direction. So that is Vx minus Vs over 2R. And in this case, what is Vx? We can write Vx in the form of node voltage, which is which it is already in Vx form. So let's write down the equation now. So this is the super node. Let me clear it. So if we apply KCL on this super node, we can see all the currents entering the super node or leaving the super node. We can consider that as an option. So in this case, KCL at Vx will be, if this is Vx, so the current leaving the node will be Vx minus 2Vs over 2R, which is this, Vx over R, which is this one. Current, it will be opposite of this, it will be minus Vx, and current going in this direction will be Vx minus Vs over 2R. We've got this expression over here. And then from this we can find the value of Vx, because there are only two unknowns, Vx and Vs. We've got the value of Vx in the form of Vs. And since we need to find I short circuit, we've already seen that expression, current entering the node is I short circuit and current entering the node is AVX. This will be equal to this current. So we can write this like this. So I short circuit is these two elements. So here we already found Vx, we substitute Vx here, we substitute Vx over here, we get I short circuit in the form of Vs. So that is this expression. So here we can see I short circuit is equal to this expression in the form of Vs, and the open circuit voltage or V Thevenin is also in the form of Vs. The ratio of the two will give us the R Thevenin. So R Thevenin is V open circuit over I short circuit, which is equal to this term. So with this, we can actually find the Thevenin equivalent circuit by replacing this R Thevenin by this value and V Thevenin by this value. So that would be the Thevenin equivalent representation of this circuit. So let's conclude the session here. In the next class, inshallah, we're going to talk about the last topic of this chapter, which is maximum power transfer theorem. Thank you very much.